Good evening and welcome everybody. This is Obi-Wan Pez for N-Simplex Pachinko. We are getting things still a little set up here. I am trying out Stream Elements pretty soon. I think it's currently technically up and running, but I don't know. Don't know if it actually works. That's not what I wanted. No, that's not what I wanted. So there's probably a lot to change with Stream Elements because I have no idea how it actually works. But at the very least, we can give it a shot and see how it works. Or doesn't. Because if it doesn't, that's important to know too. Hey Super Brain, how's it going? Okay, this is not... yeah, okay. So I've got the source up currently, but at the same time it's there's nothing that's showing up, but you know, that doesn't necessarily mean anything. So we'll just wait, I guess, and see what happens if we get somebody following tonight or something else. All right. So, as the info says tonight, we're just kind of doing our usual homework help type thing, and then also gonna look at the quadratic formula. What's that? That Stream Elements doesn't do anything until something actually happens? All right, and tonight we've also changed the background on who's its whiteboard here, so that it first of all it is graph paper, woohoo, and also it is whatever. It is first of all graph paper, and second of all it is a little bit bluish tint, so that it's slightly easier to work with that. Hey, Pro Fisher, how's it going? Maybe that also will not work. I don't know. I mean... okay. So, how y'all doing? I gotta get used to this again. My setup at work, it's the same tablet, but my setup at work is my setup at work is that wherever the cursor is, like I can lift my pen and then put it somewhere else and put it down and it stays where it is. So then when I move to the edge, the cursor just stops dead. And I'm like, right, fine. Guess I gotta recenter like every single time. Alright. So the first thing that I wanted to look at was talking a little bit again about what I do in terms of graphing, because I do things slightly differently in my class, and some of my students appreciate it, others most certainly do not. And we were talking today about, in particular, like how to graph just a random exponential function, at least in one of my classes. The other class is doing quadratics, which we'll actually talk about. But if you wanted something like y equals, that's too close. 2 times 3 to the, let's do 1, sure, why not, 1/4 x minus 3 plus 2. And you know what, let's back that up. Let's make that a minus 4, just for fun. Alright, so one of the things that I really focus on with my class is looking at the general form of what the parent function is. So in this particular case, y equals 3 raised to the x is what I term the parent function. And the parent function, generally speaking, is going to be graphed it'll, you know, this will at least make it slightly better. My graphing is, generally speaking, horrendous. Anyway, it's my handwriting is the problem. All right, so we got 1, 2, 3, 4. So we'll do 8, 16, and 24. All right, y equals 3 to the x. We were, you know, if you just look at the parent function, you want to look at the pattern that exists here, and so we could say, like, all right, we got x and y, -2, -1, 0, 1, 2, and 3. Yeah, that's the other thing. I have done that myself too. That's a real pain because trying to put it down where I can't actually see where it is awful. Like I can get close, and then it starts jumping my cursor around. I'm like, all right. All right. So 3 to the 0 we're going to get here is just going to be 1. 3 to the first is going to be 3. And then from here you look at this and you say, what kind of pattern is there? Well, in this case, moving down is going to increase our exponents by 1. So increasing the exponent by 1 is going to multiply by 3. So we get here 3 to 9 to 27. Going in the other direction, we're decreasing our exponents by 1. We are dividing by 3. So 27 to 9 to 3 to 1. Then with my students, you know, these are mostly liberal arts majors, so got to be gentle. Then we say, okay, what does it mean to have a negative exponent? And they're like, oh, you put a negative out front. I'm like, no, no. So, no. This does not have anything to do with negatives out front. We all here know that. But, you know, you got to be pretty explicit. Okay, what does it mean? We're going to keep dividing by 3 over and over again. So this includes if you go up further than this. So 1 is going to become 1/3. And -2 is going to become 1/9. So that you're looking at this and saying to them, this is going to be 1 over 3 squared, which is our 1 over, or no, 3 to the -2nd power. So it has nothing to do with a sign. It has everything to do with which side of the fraction they're on. So that's how I got them to understand this. All right, so then we look at this and we say that, all right, 0, comma 1 is going to be way down here. Each of these tick marks is going to be worth 2. 1, comma 3 is going to be here. 2, comma 9 is going to be up here. And 3, comma 27 is going to be up here. So 26, 27, give or take. And then, of course, negative 1, 1/3 is going to be like way down here. And negative 2, 1/9 is going to be even closer. And again, get them to think, what happens as we decrease our x values even further? Well, this is going to be 1/9, 1/27, 1/81st, damn it, 1/81st, 1/243rd, etc. And, you know, what is it doing? Okay, well, every time we're moving up one, every time that we move up 1 in the table, our x value decreases by 1, so we keep getting more and more negative. Our exponents get more and more negative, and then the y values keep getting cut in thirds over and over again. So then you ask them, what is it doing? Well, it's approaching 0. Is it going to reach 0? No, of course it's not going to reach 0. There's always something left over. So that little piece that's left over keeps getting cut in thirds, but there's always something left over. Yeah, so I mean, I did pick these particular x values because with all of our parent functions at the beginning of class, or at the beginning of the semester with my pre-calc class, we do all of the parent functions that are for basics. So it's polynomials, roots, absolute value, linear and constant technically count as polynomials, so we go with that. I think that's it. Yeah. So, again, big ones, polynomials, roots, absolute value. So those are the main things that we're concerned with in order to figure out, like, what are we talking about? So then the parent functions are almost always centered around the origin. So, well, those all go through the origin. So trig functions, rational functions, and any function that isn't going to be just a simple linear transformation like this, we save those until we delve into them later. So, for instance, quadratics and higher degree polynomials, we're just getting into quadratics now. And trig functions, technically, yes, you could just do a linear transformation of that sort of thing. And we could do the same with, you know, here's an exponential function. Here's what it looks like. We don't do any of that. So it's just the simple ones. The reason being that when you do the simple ones like that, they all go through the origin, and they all have an initial point of 1, comma 1. So they go through 0, 0, and 1, comma 1. And I'm trying to think if I'm leaving any out, because I'm going to sound like an idiot if I do. It's not until we get to rational functions in the next unit that we start seeing functions that don't have 1, comma 1 as its initial point. So I call, right, where's the... So I call this thing here the initial point, because it's the first one you figure out. And then here we have the origin point. So literally with every function you ever do anything with, the origin point is always 0, 0. Like, I don't care what it is. And I know the hyperbolic function technically is, you know, it has a initial point of 1, 1. But it has weird behavior, right, because of the asymptotes that are on it. So we saved everything that has asymptotes, which includes all of our trig functions, which I know you can hit me for that later. Right, our sine and cosine we still save for, like, the trig unit. The hyperbolic function we still save for later. Yeah, well. Right, and our Rusty Huts, how you doing? And our blue one here, I call the initial point. So in this particular case, and this is the thing, right? Most of the functions that I already said, the initial point is 1, comma 1. The rational functions also have, hyperbolic function also has 1 comma 1 as its initial point. Now, it also has another initial point, depending on whether it's 1 over x squared or it is just 1 over x. The initial point is either going to be negative 1 comma 1 or negative 1 comma negative 1. So it'll have 2. Oops. The initial point for the exponential function is 0 comma 1, which is weird. Right? I mean, it's different than like all the rest of the stuff we've studied the entire semester. So we kind of left exponential functions up until this point. So this is in unit, it's like the very tail end of unit 2 for me, of 4. Trig being the opener for the 3rd unit, and then 4th unit opens with law signs and cosines. And then we get all the fun applications for trig. Anyway. So essentially, yes, the students, by the time they reach exponential functions, they've been kind of trained that that all of our functions are going to be centered around the origin to begin with. And then eventually we'll find cool stuff like that. Yes. So typically what we've done is we have had like an initial, oh, by the way, here's how inverse functions work, back when we do function analysis at the beginning of the course. So like I threw that in today. And I was like, oh, by the way, I forgot this, so oops. So we did inverse functions, which included just all of the basic ones. You know, like I said, the polynomials, roots, and absolute value. And we said, okay, what do you do with this stuff if you want to find inverse functions of these? Then what we do is after we do exponential functions, we go back and we say, okay, now let's find inverses for the things that we just did, which I'm arguing with myself right now then. That's interesting. I think maybe... You heard it here, folks. Yes, we do composite functions as well. I think what I'm going to do now is probably, when we do rational functions, also say, oh, by the way, what's the inverse of a rational function? And it's another rational function. So when we're doing like graphing of stuff, it'll be a little bit easier to just work with it, go directly. I'm trying to remember where that work is in the actual. Oh no, I just realized that might be inside of. Oh man, that might be inside of. We might have rational functions inside of that section. That sucks. All right, whatever. They'll do fine. So we switched recently from... We just switched from... what were we doing? We were doing Pearson for a long time. And it was in this one order. And then we just switched recently to Newton, and everything is like out of order, and it's an OpenStax book, which doesn't cover like half the stuff I want. So at this point, I'm just about this close to saying, F it, I'm going to write my own book. Which all of you here are going to help me out. Yes. So, Pro Fisher, go for it. Rusty Hots, the x to the 0 is one question, I think is perhaps a little bit of both. So I think it depends on how you're going to define it, due to the fact that 0 in for x is going to cause a problem. However, the way that I do it in terms of yeah, just a, small little thing. God, and every time I teach it, I'm gonna change it. Oh, this is a way better explanation. All right, so if you're looking at like x to the a is equal to 1 or something like that, or I mean, it doesn't even matter. So I would say that the way that you're going to graph x to the 0 equals 1 is that you have that this is going to be a constant function with value 1 for all values of x with the exception of 0. So that this is a limit. So the limit as x approaches 0 from both sides of this particular f of x is going to be 1. So due to the fact that this is not here, right? This is not actually here. You can't have it be there. Then you've got to take the limit for that particular value, but it's 1 for all other values. So you would have to technically write on this that x itself cannot be 0, but that you know that the limit as it approaches 0 is still 1. So it's 1 for all values with the exception of 0. All right. Okay. Yeah. So that's a fun one. Doing one-to-one. So one-to-one function in Superbrain. Where are you from? Like approximately. I don't need a. Is it UK? Or no, not UK. Europe somewhere. Anyway. Yes, I would say Germany. Okay. So yeah, one-to-one is a bijection, where you're saying that you have a group of x values, which we generally call. Oh, you know what? That's good. X will belong to big X, and Y belongs to big Y. Then your function maps x onto y, and your inverse function, if one exists, will map y onto x. So in order for us to have this property that we have a function which also has an inverse, which is also a function, we have to have this one-to-one property, which I think bijection is probably the best term for it. I'm pretty sure that's correct. Pretty sure that's 100% correct. But they don't learn that term until they are in a course that is called discrete structures in my school. Yeah. I mean, I understand, because we do this in our math majors course, but the problem is that these are like these are linear, or these are students who are not going on to do any more math in some cases. So like this is it. And to give them a word like bijection, or to say you have a domain and a codomain, like they would just not understand this. And I mean, yes, I can give them a little more faith than that. But generally speaking, the audience that we are serving in the pre-calculus classes are not going to be interested or care or want to understand the difference between a domain and a codomain, nor between a domain and the 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 difference between an image of a domain and a codomain, which I might be getting confused myself because, like I said, I only actually did this in my majors classes, and it's been like almost 20 years. So, yeah, and I mean, they can suck it up for a semester. But at the same time, like, there's been a lot of. I think the problem is that there's been a lot of sliding over the decades where, the teachers in high school are trying to use simpler language to help the kids understand it. And because of that, then the college teachers are trying to teach, the high level language, and they're going, what? Like, I don't understand what that is. This doesn't make any sense. I know this word. And then the college teachers go, all right, let's use that word to, and so it's been a little bit of just this sliding. No, it's fine. So a one-to-one function is one where, what is it? Any all elements of x have exactly one unique element of y. And you know what? Let's get rid of have. That's a silly word. Yeah. All elements of x map exactly to exactly one unique element of y. So I think that should probably match bijection. I hope. Let me know. All right. So then, right, where was it? Horizontal line test. Right. So, so what we're going to do to test whether a function is one-to-one is to say, okay, we know. Hey, Brad. All right, let's try this again. So, here we go. If f of a is equal to f of b, then a equals b. All right, and this has to go the other way too. So technically this is if and only if. So yes, bijection. Oh man, guys. I completely forget the injection surjection stuff. It has been so long. That definitely is in the discrete structures class, and I have not taught it. My former dean from this past couple of years was like, "We got to get you to teach that class." I'm like, "Yeah, I would love to. I'm gonna need like, a year to prepare it and probably sit in on your classes." I ended up not going, or not. He ended up not assigning me, so whatever. That's the other thing is that he loves that class so much. He like always had to teach it every semester, and it's a really good class. I do actually wish that I had taught it, but maybe sometime in the future. The problem is that there's like an 8 o'clock class and an 8 o'clock class on the two ends of your day. So pick one or the other. You're either going to be up at 6 a.m. getting ready for an 8 o'clock class, which I can't do because I got kids that I have to take to school, and they don't let them in until 9. Or I have to go at 8 p.m., at which point they're going to bed, which I'd much rather read books to my children. No offense. So like, yeah, it kind of sucks. It's you got to choose one or the other if you're going to teach that class. All elements of big X have a unique f of x. Yeah, yeah. So yes, that would be the definition of one-to-one. Or at least, hang on, that is the definition of one-to-one as long as f is truly a function, in which case that covers the surjection, I think. Probably. Verify that. Anyway, yeah, so it's probably like all of it. So anyway, f of a equals f of b if and only if a equals b. So the backward one, so a equals b implies f of a equals f of b, is just the definition of function. So we already said that f is a function in part of our definitions, so we just say, all right, we're good. The other thing that you have to prove then is that f of a equals f of b is going to imply that a equals b. All right, so that's the slightly more challenging one. So if you pick just literally any one-to-one function, a function that you know is one-to-one, like, all right, let's do this. Let's see, f of x equals 3x plus 2 over 2x minus 5. Say, I want okay. Woo. Okay, so sorry about that. I was just checking something. Okay, so with a function f of x equals 3x plus 2 over 2x minus 5. This is a one-to-one function, and at least I know it's a one-to-one function. So if I want to prove it to you, I've got to show you that, yes, in fact, this is going to end up yielding if two... oh, man. Yielding that if two function values are the same, then their input values must be the same. So here I'm going to say that we want f at a equals 3a plus 2 divided by 2x minus 5. Nope, 2a minus 5 equals f at b, which is equal to 3b plus 2 over 2b minus 5. This one requires a little bit of work. If you just do something with like literally linear functions, it's much easier. So if you want to do some proofs with linear functions, you can grab those pretty easily. We can also disprove it for something like a quadratic function, which would be really nice to, we'll do that next. So here f of a equals f of b. We've got to prove that a equals b. So here we've got two functions that both have denominators, so we can multiply by the stuff in the denominators, your least common denominator, in order to get the stuff out. So this would end up being 3a plus 2 multiplied by the 2b minus 5. If I hear any one of you say cross multiplication, I swear, equals 3b plus 2 multiplied by 2a minus 5. Now, it is a term that I have banned in my classes because they use it so frequently. It's wrong. I allow them to say FOIL, but I don't do it. I call it double distribution, and they get used to it eventually. All right, so if we multiply all this stuff out, oh, yes, literally, FOIL here. So I do double distribution for them, especially, again, for students who are a little bit weaker with their algebraic skills. Like, don't just do this automatically because you will get something wrong. I encourage them to either do the box thing, which is you're multiplying 3a plus 2 by 2b minus 5. Ugh. I keep shorting these with my hands. All right. And then here, we're going to multiply each of the column and row headings to get the stuff in the middle. So this is going to be, nope, not 3. This is going to be 6ab. This is going to be 4b. This one's going to be negative 15a. And this one's going to be a negative 10. So I tell them to do this. Again, you don't have to, obviously. It's just, it helps organize if they don't know what they're doing. So again, 3a times 2b is going to get you 6ab. 3a times negative 5 is going to get you a negative 15a. 2 times 2b is a positive 4b. And 2 times negative 5 is a negative 10. Equals. And same on the other side. This is, again, a 6ba, but really I could just do this as a 6ab because they are commutative. 3b times negative 5 is going to be a negative 15b. 2 times 2a is going to be a plus 4a. And then 2 times negative 5 is a negative 10. Absolutely. You'd have to do it in 3 dimensions, but yes. or if you wanted to do 3 binomials, you could also do 2 at a time. Right, so do these 2 first, get this stuff, combine like terms, and then put the other one on. So do it as 2-dimensional slicing, or as literally a 3-dimensional... Yes, attaboy. So Brad, this is strictly for organizational methods. You don't have to do this, like I said, but it does make it kind of nicer. And like Pro Fisher says here, if you try to do it in terms of 3 binomials, you might have a little bit of a problem. Because literally, you would have to do this out as a cube. And then I'm having a problem here because now this is going to be like, there are going to be 8 cubes, so like this would have to come forward here, and it's just going to make a big mess. I mean, eventually I could erase some of it and make it slightly nicer, but at the same time, it's just going to be, it's going to look awful. See, this is when you get 3D modeling software and you do it in there instead of... All right, anyway. So here we've got this stuff. And then, yeah, my name is not, or my channel name is not NSimplex for nothing. So, so here we've got a subtract 6ab from both sides. We've got an add 10 to both sides. So that's gone. This is going to be a, well, I might as well just do this. So I'm going to move all the a's to make them positive. So plus 15a, and make all the b's positive if you can. In this case, you can. Plus 15b. So all this stuff goes away on its various sides, and you get a 19b equals a 19a, which then means that b equals a. So we're good. Okay, it's that one. I was wondering which smoke detector it was that was beeping. Just give me a second here. Unfortunately, it's the one right above my head. All right, next question. How do I get this down? There we go. And boop. All right. Well, there's one problem solved for the night. So yeah, Rusty, you can go either way with it. I tend to take the first thing and multiply it through. Like I said, I tend to say this is going to be, whoa, that's not what I want. 3a plus 2 is being distributed in, so multiply by 2b. And then this is a little ugly because you stick the negative out there, or you can put a positive in between them and then have the negative 5 just be at the end. So 3a plus 2 times negative 5 like that. So you can go either way, but you know, I tend to do this, and I don't know if that's just me saying you're going to take something and just keep, you know, distribute whatever's in front. But either way. Yeah, that's the other thing. Brad's got it. So yeah, but the other thing is, like, if you have a group of algebra students, generally speaking, they're not going to be doing higher dimensional multiplication in the first place. So most of the time, they're going to stop after 2. The pre-calc students do have to multiply through, like, you know, larger polynomials. So like 3, whatever, I'm stuck on this. 3a minus 2 times 5x, wow, plus 1 times 7x plus 3 times 4x squared minus 1. You know, they have to do this and, like, get the, or my students don't have to multiply this out, but especially if it was like, is greater than 2. Then they're like, because you have to multiply all this out and then subtract the 2 and then put it back together again. Yeah, in this case, it's probably not going to work. It's going to get nasty. You're going to get nasty irrational roots for this. But so I tell them, you know, I've worked stuff out, right? So eventually they're gonna get some at least sort of nice polynomial type stuff. Yeah, so this is one thing that I have been trying to do, you know, as a teacher, as specifically a math teacher, and specifically in a math teacher who has himself struggled somewhat with some topics, is like, I really dislike running out there and just being like, here's a formula, because that happened to me so many times. I cannot tell you, even in, or especially in, perhaps, my master's level stuff. They're like, here's a thing. And I'm like, but where did this come from? Like, why does this exist? And the problem with my master's classes especially was that these people were not teachers. It was billed as these people are not teachers. It was like a selling point. And so the program was for people who were like working full time. So it's an evening program. It's at a prestigious university, but it's a satellite campus. And the satellite campus is at a place where they have a physics lab. And there's a lot of people there who have like, really awesome projects they're working on. They're doing security clearances, they're doing really high level math, but at the same time, they're not doing like high level research in like theoretical mathematics. So, unlike the professors at the, Ivory Tower University kind of thing, um, they have a little more down to earth like application. And so there's good parts and there's bad parts. The good part is that they have the application and they know what they're doing like with this stuff. I know that this partial differential equation is going to be used in signal processing, so you better know how to do this if you're going to go into signal processing, stuff like that. And I went into this program as someone who had been a teacher for already 3 years. So I had been teaching for 3 years by this point, and I came to this thing, and they started teaching the subject, and I'm just like, oh my god, you people, like you're not good teachers. And I'm like, can so I'd like delicately um, ask questions that I would be asking were I to teach this class, and like trying to lead myself and my fellow students through something. So the problem that I had, and maybe it's easier to define what a bad teacher is in this particular case, or to show you a counterexample, right? I did not like the fact that they read straight from the book. I was supposed to go home and read the book between every class. So why are you doing examples from the book that I was supposed to read? And most of the time I read it because I had not been a very good student in college for my bachelor's, so I knew that I was going to have to damn well push for this. Because again, this is a somewhat prestigious university. I went to a state school in New Hampshire. It's the University of New Hampshire. I usually wear my shirt too. Um, Kula Yellow, how you doing? If you have any questions, let me know. But yeah, I went to the University of New Hampshire for undergrad. It's, an okay math school. It is not Chicago University by any means, but they did all right. The people there, I really like the way they teach. They got me curious. They got me interested in doing stuff. When I went to the prestigious university satellite campus and had applied mathematicians and physicists and all these other people teaching my courses, what they did was, again, they read straight from the book that I was supposed to have read. They stood up front and did examples, like one right after the other, without really explaining the concept. So again, it's applied, but like I didn't get the theoretical stuff, which I sort of needed because I didn't. And then when they did have like, here's where it comes from, it was maybe a derivation, but it wasn't really an explanation as to like how the derivation works. So when I'm teaching, and I don't claim to be the best teacher out there, I am not by any means. So I go through, I mean, anybody who's been here a while has seen it. I will start from some sort of basic principle that you know, and then I will start building off of it. I really like when I'm with a whole bunch of students, I really like to ask a lot of questions. So I am guilty. I do mostly the Socratic method, which is basically like, here, let me ask a question that will give you like a breadcrumb that you can see. It's pretty obvious. I try to ask only obvious kind of questions. And it's like, okay, here's the thing that you can figure out. you know, when we're up here, like, what's the definition of a function? Oh, look at that. We've got, this thing is the definition of a function, so we've got one condition checked. Now let's go and do the converse of this. F of A equals F of B implies A equals B. Okay, where do we start? Then they go, okay, what's F of A? Write that down. What's F of B? Write that down. And it's very interactive. So the pandemic was really hard. Not for the least, not the least problem of which was because like 99% of my students left their screens blank with their name on it. And I was just sitting there going, yep, I'm asking a question and y'all aren't answering. So it was just really rough. There were like one or two students in every class who just would answer every question. And I'm like, can we get maybe 3 or 4 more people? Yeah, okay. Brad, that could be interesting. I haven't actually tried that before, but if you if you take the programming route, right? Students will understand that generally speaking. So I have not seen it as a part of any other curriculum. So if you treat it like a definition or like a assignation that you are assigning f of x to y, um, like that works. But at the same time, when you're stuck in the middle of a problem, like this part here that says that this thing is equal to that thing, that's more of a. So what I try to do with this is, in this particular context, this is not an assignation, but rather it is a just relation. So it's giving us a relationship that exists between these two things. So in the case of, f of x equals this stuff, A, that is an assignation, but it is also a relation. Yes, you all are just blank names here. However, the people that I can't actually, like, see in chat, I will never know that you're here, not here. Uh, at school, however, I have a list of participants in my Zoom call. It is a list of participants with their names all right there because I need to know whether or not they're there. And I have to keep a legal record of who is where at what time, just in case anybody decides to throw a subpoena our way. Right? That is, in theory, is a thing that could happen. Like, oh, this person was, out robbing a bank at 12 o'clock. No, they were in my class. Thank you very much. Um, Now, if they're not participating, I can't guarantee that they weren't. But, this person was in my class. They, came in at this time. They left at this time. That I have to keep a legal record just in case. So Rusty, yeah, that was also. So actually, I should say that that was not entirely my experience, but yes, I can completely understand. In my 300, 400 level classes, I was not a math major. And so most of my professors were not necessarily pure math researchers. And because they weren't researching in pure math, a lot of them actually did have a lot of connections with applied, and a lot of them had connections with math education, which was my major. So I had several teachers who did, you know, other kinds of research other than just like, here's some crazy high level stuff that you're never going to see unless you work on your doctorate with me. Like, I did, however, have one guy. This was the University of New Hampshire in 2000. Well, okay, in like early to mid 2000s. Um, so his name was Robert Jacoby. I will say that he has since passed away, so I can, you know, I will out him as being one of my teachers. So he had quote gotten his doctorate in the 40s, and this was 2000 and you know 2000 to 2005 ish. So he'd been there a while. Anyway, he was teaching my linear algebra, senior level linear algebra class, and I did not understand a word he said because what he had done was he had created his entire world of linear algebra all around everything that he had like researched over the years and stuff like that. So I was never in the class where he taught Jacobian matrices, which is too bad. Um, but probably my spouse did because she had him for um, the sophomore level linear algebra. So maybe. I don't know that she had him for either differential equations, or I don't think she had him for either differential equations or multivariate calculus, which would have been the two classes where they used Jacobians more. But yeah. So anyway, he had a way of sitting back in his chair and just kind of relaxing like this, and he had his whiteboard markers that he had, and his eyes were like almost entirely closed. He was not sleeping. Okay. He was completely awake, completely aware of everything that was going on in the class, and he would just kind of write on the whiteboard behind him like this, and yes, literally behind him, um, and lean back and actually occasionally put his feet up on the desk, and he would ask us like, what are the structures that we see in linear algebra, and he would not use the standard language. So, like, the standard language is that things that have parentheses around them and are x, y, and z are considered coordinates. And so you would call them coordinates. But he said his idea was, well, it doesn't matter what you call them. It's XYZ stuff. And then he would go on and do something else. And then he'd talk about then he'd talk about like the span of a set, right? The span of a particular vector. Yeah, span of a particular vector, and talk about vector space and all this stuff. But again, he did not use that language. It was completely different language, and I'm just like, I, I, I just don't get it. So that's part of the problem. Is the language that describes mathematics can change depending on where you are. Um, which we already did see that a little bit earlier, right? Because, Superbrain, you're from Germany. You don't necessarily see all the things that we see here. So, one-to-one functions, right? Although you can call it bijective. And it works as long as you know the technical language for it. So, yeah, we can all thank Euler, or perhaps curse his name, whatever you prefer, for coming up with all of this particular notation. But yeah, so he would write on the whiteboard behind him. He'd do all this other stuff. He was an amazing individual to have as a teacher. I just did not get him. But my spouse, thankfully, was also in the exact same class that I was, and helped nurse me through this. Like, okay, let's talk about this. So we'd spend like an hour or two every night doing the homework, like just sitting on her bed, face to face. Let's talk about this because I just don't get it. So she definitely saved me in that one. I got all the way through the class. We had an oral final exam. Yep. So I had a half an hour to sit in his room face to face, and he just started asking me questions like, "Hey, so what is this? So what is this? What do you start with when we're talking about this other stuff?" And I'm just like, I don't know. And then he like kept getting more basic with his questions, and I'm like, "Oh, this is awful." And probably about 5 minutes in, he finally asked me a like question that I started getting answers on, and he was like, "Okay, now let's start from there and let's start building on that." And I got to the end of our time, and he was like, "So, I think I'm gonna give you a B." And I'm like, "Take it." Man, I thought I was gonna fail that class. But I mean, I had at least done all the work. So, like, even though I didn't do very well I did not do well at all in the final. And I, did not do terribly well on the, like, one exam we had at midterm. Um, I did moderately okay for that stuff. And I got all of my homework in or almost all of my homework in on time. Yeah, so and that goes back to Pro Fisher's question too. What's the best way to integrate Socratic method into the virtual class? That's hard. All I really can do is like try to engage all of the students, like try to make them interested in keeping their cameras on and like, you know, stay either muted but with their finger over the button so that they're actually prepared to answer a question, or just unmuted if they don't have anything else going on around them. Like if they're in a quiet space, that's fine. At least that's fine for them. And right now I have, one particular uh, student who is like answering everything, and I'm like, give a little bit of space for everybody else. But at the same time, again, everybody else is not responding because he's doing it. And they're just like, that's an expectation. I can have him do it. But I will say this particular class is really good in terms of interaction. Like they'll chat with each other for a couple minutes, and I'll just be like, all right, cool. It yeah. So they did all right. They're doing okay so far. So like I interact with them. So here's the other thing is that 3 of my classes are in person, 1 of them is virtual. So the virtual class is a bit of a challenge, but like I said, we're still in September. Everything's going okay so far. As long as I can keep them interactive, and hopefully I'm not going to have like, half the class fails the exam or something like that, and then they all just shut up, because that would be awful. I don't want that. Um, but more or less, the class goes like this, except a lot less interaction, because they have an agenda, right? They have to get through a certain place by a certain time. Us here, whatever. We'll go off on 50 different tangents and come back later. Maybe we'll cover this next week. Maybe we'll just run late, right? Maybe I'll stream for 4 hours because I don't care. This is exciting. But yeah, right? With them, I have a set time frame and I need to be somewhere. I need to get somewhere by some time. So it gets a little hard sometimes to try to have a discussion, but then at the same time rein that discussion in and be like, okay, now let's move on and try to get to the next thing. Yeah, I did not have a great time. Well, I mean, that linear algebra class, like I said, was a challenge. And real analysis was, for me, a bit of a challenge. So, Messy Sucker, by the way, thank you for coming. Welcome. So, yeah, I had a bit of a challenge in real analysis. I got almost everything he was saying, but at the same time, like, I was struggling on the homework because I just couldn't visualize some of the stuff that was going on. Like most of the like oh, now let's look at some arbitrary epsilon around this individual point and then what's going to happen. I was like, yeah, I got that. That's no problem. But there was something a little bit later on that I was like, I'm not getting it, and it was really rough. So my school is not a K through 12 institution. It is technically a public 2-year school. So we're open to the public, but it doesn't mean that literally everybody goes through our doors. Um, so it is, yeah, it is a college, 2-year college. um, or I guess one of the ways that I could say it is that our institution accepts public monies. So I mean, most of them do, but we do get. Uh, no, I do not need to get a teaching certificate in order to teach there. Many of my colleagues have been through the public schools and have had their teaching certificate at some point. But many of them also just started teaching at a college, whether that be their university that they got their degrees from. They were TAs, they were postdocs, they were, instructors at those locations, whatever it may have been. um, oh no, no problem. So some of our students or some of our colleagues are fresh out of college. They got their bachelor's. They don't have a teaching certificate. That was me. I was actually working toward getting my teaching certificate and taking one class every semester and working in a public school. So I was working at an actual K through 12 in secondary. My major was mathematics education at the secondary level. So I did get a bachelor's in that, and I was intending to work in a K through 12. But one thing led to another. I ended up getting all 4 of the classes that I needed to get my teaching certificate, and then I was like, eh. um, I think the straw that broke the camel's back, so to speak, was the fact that I had 2 letters of recommendation that I had like worked really hard to get because these people were just not writing them, and I was like, look, dude, I need a letter of recommendation. Please get it to these people. You need to send it. So I'm sending like basically a weekly email to these people, and they could have at that point they could have blocked me and I would have never known. But I eventually got all of my letters of recommendation in. Then I needed to finish my 4 classes plus finish my internship year, because what you do is if you work full time with a contract, so you are contracted full time in a K through 12, then the people who are there will allow you, or the Department of Ed will allow you to finish that year and count that as your internship instead of like trying to get your master's or trying to get your teaching certificate, like doing 1 year in a school as an internship. You can do that as a paid job. Hey, Brad, thank you very much. That was a few too many clicks for some reason. I'll work that out later. Yeah, I know. I was surprised because I was like, oh no, it's not gonna work. Oh, you know what? Is it because it's not on the other one? Or is it because it is on the other one? I feel like that shouldn't matter. Can I disable it? Anyway. Yeah, I'm trying to work out to make Stream Elements do all the stuff that it's supposed to do. Um, it doesn't have the chat, which Like, I don't care all that much, but at the same time, like, that was supposed to be over there. But, whatever. I'll figure it out later. mm. Some of the states are pretty difficult. So I was doing this in Maryland at the time. And so I was like, I needed my four. So I needed my problem was that I needed four classes on top of what I had already taught because I hadn't done the four classes that they particularly wanted in the state of Maryland that the state of New Hampshire did not have. So it was like, had I gotten my teaching certificate in New Hampshire, I might have been able to make that work in Maryland, but there were, like I said, four particular classes that they might have just said, like, no, you can't do it. You still need to do all these things. But yeah, they looked at my credentials and were like, you're not there. And then the problem was that after I'd finished all four of my classes, I went back and said, now? And they're like, your letters of recommendation have expired. And I'm like, so I was just like, no, that's it. I'm done. I can't do this. This is. So, like, I probably would have gotten glowing recommendation, or I did get glowing recommendations from my former bosses, or at least two of my former bosses. Uh, and, like, the one that I had just left from probably would have been okay, but she did not like my teaching style whatsoever, and I was not going to dance like a trained monkey like she wanted me to. So I was like, no, no, I'm not coming back next year. And she's like, all right, fine. Like, thanks. Yes, I have a much better job. It So actually, I mean, I ended up taking a hit for a little bit, but I was expecting that. I was working as an adjunct professor, so I was only teaching one class a semester at the school that I am at now. And I also decided that, well, clearly that isn't going to be enough for me. So instead of taking multiple adjuncting positions, which some people do, and no disrespect to them, but that's not really what adjuncting is for. Um, yeah, I got you. I'll come back to that in one sec. But yeah, I was an adjunct for 3.5 years, give or take. And I was also working as an insurance credentialing data entry type person. So I worked for a particular company and also at the same time was working on my master's. So I was, my spouse was like, hey, I'm going to start working on my master's soon. I'm like, well, let's see if I can do it. So that was when I started working on my master's, and I was shocked that they let me into the program, quite frankly, because again, I had like a 3.0 average. It was okay in my BS, and it had been 2 years since then. So like I'm okay, but I was not a great student. And then I got to this, I mean, I don't know if it's Ivy League or like, just really prestigious, but either way, it, it's this big name university, and they were like, "Oh yeah, you can come in as long as you take like this one class to make up for the class that you didn't do so hot in college." And I'm like, "Deal." So after I got my master's, that's when I started working at the school I'm at now, and it's the same place that I was adjuncting at. Yeah, I love it. I was offered a position at the same salary level that I would have gotten had I taken my master's and gone to the fraud detection department inside of the same company that I was working for. So I could have gone either way. I had a fork in the road here. Am I going to take this corporate position, which is going to use my master's education in neural networks, which is really cool, and like, it's cutting edge, and it's probably going to pay really well very soon. I probably would be making at least 20% more of what I am now, but like I'd have to abandon teaching. Or at the very least I'd have to cut back to like teaching only one thing. Yeah, who knows? I could have maybe joined up with the physics lab there and started teaching for them. Uh, but anyway, yeah, so I ended up going the teaching route, and again, I absolutely love it. It's great. So as far as Common Core is concerned, right? Everything that I have seen out of Common Core, all of the materials that I have seen teach all of that stuff in a very sometimes non-intuitive but very helpful way that will prepare these students, if they get it, for algebra without them even knowing it. So for instance, the like breaking stuff up, doing addition, like 3219 plus 7843 plus 6211 plus 1213, right? Let's add up four numbers. Now, some people might be like, "Oh, F it, I'm just going to get the calculator." Like, you can do that, but then the problem becomes you got to understand that this is actually not just four individual numbers, but you can break all of this stuff up by saying that this is 3000 plus 200 plus 10 plus 9 plus 7,000. I'm going to regret this pretty soon. Plus 800 plus 40 plus 3 plus 6,000 plus 200 plus 10 plus 1. Is this a really long and stupid way to do this? Absolutely. However, it actually assists you much more in understanding algebra later. So everybody's like, well, just put it like this. Do the 3219, 7843, the 6211, and the 1213, and do it like we did it, right? You just add up the first column, put the tens up there, do the second column. Like, you can do that. It's valid. It works. But it doesn't help you understand what this is really doing. Like, it doesn't help you understand this at a much deeper fundamental level. It gets you an answer. Okay. This right here, this is preparing you for like 3x to the third plus 2x squared plus x plus 9 plus 7x cubed plus 8x squared plus 4x plus 3 plus dot dot dot, and finish the rest of them, right? X equals 10. Ta-da! Right? X equals 10 gets you exactly all of this. And it's going to get you the exact same answer that you would get if you actually added all this stuff up. Right. It's about knowing what to do rather than just to get an answer. So the United States has been very much focused on getting an answer for at least 50 years. If you've seen The Incredibles 2, right? Y'all know what I'm talking about. In The Incredibles 2, there's a scene where Bob Parr picks up the book and he's like, how do they change math? Math is math. And it's new math on the front. Well, new math in the 70s was a brand new way to teach math, which was supposed to do the same thing as Common Core back in the 70s. It was supposed to teach kids at a much more fundamental level what's really going on behind the scenes. And at some point in the 70s, 80s, somebody said, "No, F this. We're just going back to the other way to do things." And they were like, "Here's how to do things by rote memorization." And again, get an answer instead of understanding. Yeah, my parents cracked up at that because they actually lived it. I cracked up at it because I'm a teacher who understands Common Core. So my biggest problem with Common Core is that people don't understand it. And I mean, not just parents who shouldn't be helping their kids, the parents should be helping their kids, but they should not be doing their kids' homework, even if it is in parallel Like you want to understand it, cool, but you better really understand it. Like go through the whole process. Do not, under any circumstances, those of you who are parents out there, or those of you who are going to have parents, do not, under any circumstances, tell your kid, just do it this way. No, no. If you have to go through and like ask a parent how to do something, or, and here's the reason why he did it, go on to Khan Academy and look at the section on Common Core, because Sal Khan went through every single grade level and he made brand new videos that corresponded to every single section in math. Sal Khan knew exactly what he was doing with that. He said, people don't understand Common Core, I'm going to explain it. And he does a really good job at least getting somebody like a basic understanding of why Common Core does this thing. So my kid's in 3rd grade, she's doing 4th grade math, and at this point, because of the pandemic, they're just like, everything's messed up. So they're just trying to, like, her teachers at that level are like, let's get back on balance. Let's not even worry about where we are. Let's try to make sure that they understand the 3rd grade stuff really well before they move on to the 4th grade stuff. Because she was coming home every day super stressed out, like right at the beginning. So, and then she was like, I don't get it. And the teacher's like, so what don't you get? And she's like, never mind. And that was her experience every single day, when she was just going in and being like, nah, never mind. I'm not going to ask my question because I just don't understand. And the two of us, we're both math people. I mean, I'm a math teacher, and my spouse is a mathematician, or was a mathematician. Anyway. So, like, come on, man. Let's figure this out. And she was just like, no, it's fine. I don't want to do it. And we're like, no, okay. Now you have to sit down. Now you have to sit down and talk with us about this, because it's not going to work if you just like, no, never mind. That's no, not in this house. So, yeah. So the other thing is that they also go back to, like, even in kindergarten, right? My son is in kindergarten, and um, his sister also had this experience several years ago, where this particular teacher just kind of like is working on stuff with some of the kids, and they're doing breakouts, and then the rest of the kids are just given like a box of stuff to just like make patterns with, but it's so unstructured that they're just like, I'm gonna play with dinosaurs, and like they're not doing the math, and it's like, so I think that they've gotten a para educator in there who at least like knows how to kind of focus the groups and be like, okay, let's talk about this. You know, how can you arrange them in like rows and columns to make like an arrangement? So one of the ways, she was like, why don't you line them up? And so, you know, my son was lining them up, and they're like, oh, well, can you make more rows? And then they'd start making more rows. How many are in that? And they'd start counting. Okay, now we've got like a little bit of foot. Oh, hit something. All right, there we go. So, you know, she got them a little bit focused. So I'm really grateful for this paraeducator to be there, because my daughter, when she was in that class, she was in the same class with the same teacher, did not have a paraeducator, and was just like so unfocused. And we're just like, what is she doing? So I went in there at one point. Yeah. I went in there at one point, just, you know, as a parent. So I read a book, I sat there, and I played for a little bit, and was just like talking with her and her group mate, who was also a kid of one of our friends. So like they were in a group together that day, and so I was just talking with them about math. And you know, I tried to do the thing where you're like, oh, can you arrange them in rows? Can you do this? How many are that? you know, and trying to basically get a sense of multiplication without being like, let's multiply. No, we're not going to play that game. Um, it actually, in the summer, I think it was the summer of 19. Yeah, in the summer of 19, my daughter was allowed to go to like a special uh, like camp activities during the day at my school. So it was like ages 6 through whatever, and so she was there. Hey, silence, or rather, should I say 9, 6? Um, did I get it? So yeah, so she got to do this camp, and so she picked like one of them was making videos, and one of them was like playing with Legos to do something in particular, like robotics or something like that. So she was in these camps, and then for lunch she would come and sit with me, and we'd have lunch in my office. So it was really cool. I've never had anybody in my office for lunch, let alone my kid. So um, we had a good few weeks in the summer there where we were just chatting and having fun. And then she was like, "Can I do some math?" And I was like, "Obviously, you can do some math." So I gave her a worksheet of uh, damn it, Pascal's triangle. So I was like, "Well, what happens if you have like you got a bunch of zeros out here? You put a one in the top one." And this is after kindergarten. I think before first grade then. And so, I asked her that, and she started filling it out, and like, oh, I get it. And then we do this, and we add these together, and you get different numbers. So she filled like the first 6, 7, 8 rows of Pascal's triangle by herself, and then started asking for help. And I'm like, oh, absolutely. When you get to double digit at addition, when you're not even in first grade, like, okay. So I helped her. I helped guide her through the bottom row of this thing, which was I think 12 deep or something like. I mean, it was ridiculous. She was never going to be able. Her limiting factor was her handwriting because she wasn't able to fit things into these tiny little hexagons. Anyway, um, so 9, 6, we are in a crazy space today of just doing whatever comes to our minds. Yeah, really, like the problem kind of got obviated further and further when we started seeing. Um, I got to read the rest of that in a second. um, so, yeah, the problem started getting really big and really like became a big problem when we started seeing No Child Left Behind come out. I mean, first of all, the intent behind that legislation was just like, whoa, it was insane. Um, the intent behind the No Child Left Behind legislation during the W. Bush years, I now somebody might call me crazy. The intent was to bring privatization to the public schools. All right, so hang on, let me let you sit with that for a second. All right, so anyway, now that we're getting political, uh, yeah. So no, the intent behind that was to start increasing privatization and start increasing the possibility for private schools like charter schools to start extracting money from the public space, and it has been successful in that particular regard. So, um, so I personally am quite offended at the entire notion that this is even a possibility that you would take public money to fund private schools. Like that is not at all acceptable to me. Um, but hey, I was intending to be a public school teacher. I've been trained up for all this stuff, so maybe that's a me thing. But yeah, I do not accept that. I do not accept the premise. So, so 9-6. Unfortunately, you just got caught in on the tail end of that. You came in on the tail end. So basically, if you can't see it, but it'll be on the video on demand. But the short answer is, I think that Common Core, generally speaking, is very well intentioned by the people who have crafted it. It explains things very well if you understand it. And the teachers that teach it need to nail it down and have it 100% all the way through and understand exactly why it is the way it is and what it is doing all the way through algebra. So some people have been like, well, why do elementary school teachers need, pre-calculus? Why do they need to get up to pre-calc? All they need to teach, I mean, even no, they don't even need to go to pre-calc. Our elementary school teachers need to get through their gen ed math. So for us, that is the course I'm teaching now, math literacy, maybe statistics, maybe they can do pre-calc, but none of them choose that. Unless they've already taken pre-calc, in which case they're like, I'm going to get an easy A by doing the class again. But they need, right? So they need to go through a set of 2 courses called Teaching in Mathematics, or The Mathematics of Teaching, which teaches them basically everything that they know through, like, it teaches basically every math that you could possibly teach in elementary school. So up through GT 5th grade or whatever. So in some cases that could be like pre-algebra. And so I didn't have to take that class because I was teaching secondary and I had to take a lot of other classes. But oh, Common Core, right. um, at this point, the children who were started on Common Core in kindergarten and know no other method of teaching must be pretty close to graduation by now. The ones, I can't remember when this was. It was probably 5 to 10 years ago. Yeah. Somewhere in that neighborhood. So 5 to 10 years ago, my spouse has a friend who is a 5th grade teacher. And she said that, math, specifically math, she said that the kids who were in her 5th grade class that year that had not been taught any other way, so they only know Common Core, just intuitively understood everything she was teaching them. And it was bizarre because she said it was night and day, even from the previous 1 year when the kids from before had, maybe it was 1st grade, where they switched, where those kids, the kids who had just left to go to 6th grade, had switched. So like they had done 1st grade in Common Core, or no, they did 1st grade in whatever they had beforehand and 2nd grade in Common Core. And like it was such an insane difference between those 2 classes, and she was just shocked that like everybody who had then learned everything in 1st grade by Common Core was now in this class in 5th grade, and she said they just got it, just every single student. And she was just like, what is going on? But it was, I mean, this is an anecdotal piece of evidence, right? It's one class, it's one teacher. Who knows? But I will say, like, the stuff that my daughter gets, she gets it, like, all the way through. And I could probably teach her some basic algebra that she would just get. And again, stuff like this, where, you know, this number, 3,219, can be broken up as 3x cubed plus 2x squared plus x plus 9, where x equals 10. And then you just change it, right? So x equals 1, what do you get? And then you can add those up. And you could, in fact, come up with anything in just a different base. And say, like, okay, if it was base 8, octal, then what is this going to be? With the exception of 9, it's literally going to be the same number. So, like, what is going on? And that's the other thing, too, is that some of these kids work off of different bases. I mean, some of the lessons work off of different bases. They're like, well, doing it in different base just means that you're going to use a different set of numbers, but the math is still the same, right? So all of the math ends up working out exactly the same. It's just that it's going to be in a different base. All right, going back to Brad's comment. Rote memorization is measurable and provable. Yeah, that's also true. Unfortunately. Hmm. Okay. So I can understand that, where they have no real facts to build it on because they weren't forced to remember their multiplication table or the fact that, this plus that equals stuff. So yeah, that could be interesting and challenging. So I'm gonna be I'm gonna be that guy. um, so 9-6. One small thing. The phrase black magic. You might want to think about the origins of that phrase. Just gonna throw that out there. So I am gonna be that guy tonight. But moving past it. So the other thing that Brad, my neural networks knowledge has come in handy. It's kind of an interesting connection. Is that my neural networks professor ended up connecting. He ended up connecting the fact that our minds work a certain way, right? He came into the class at the very beginning saying, "Here is how biology works, like neurons in biology," and we started with that as our basic principle, and then saying, like, basically we're modeling a computer system after that. We're going to start modeling the computer system after nature. And most of the best technology tends to model nature because nature, honestly, has been working at this for many millions of years longer than we have, or billions in some cases, depending on what you're talking about. So, one of the things that he had said was our brains tend to want to warm up. So, what you need to do for an exam is read through every single question on the exam first. Don't stop. Just read them. Don't do anything else. Just read them. And then, once you get to the end of the test, flip back to the beginning. Then, take your pencil and start making little notes. Do not spend more than 2 minutes or even like 30 seconds. Don't spend more than 30 seconds on it unless you're absolutely positive about how to do a problem. And if you're absolutely positive about how to do a problem, skip it. make a little note about what you need to do or put a check mark next to it. Say you know how to do this. Flip to the next one. If you don't know how to do a question, you start writing just, again, 30 seconds worth of notes, flip to the next one. 30 seconds worth of notes, flip to the next one. Go through the entire exam this way. Flip back to the beginning. Now start working on it in earnest. Every question that you just know how to do, finish it. If it's going to take you more than 10 minutes, skip. Or, do like a couple minutes worth of work and then skip. Once you get to, again, a problem that you are stuck on, where you're like, I know how to do this, I know how to do this. Oh, I can't do it anymore because I can't remember. Skip. Move to the next one. And do not stop. This was a completely insane idea to me. I was just like, how am I supposed to do this? Because, like, I don't, yeah, kind of like I don't have that kind of time, right? You're sitting there thinking to yourself, I don't have this kind of time. But actually, I sat down at my midterm and I almost went into a panic attack because I did the same thing that happened to me in linear algebra, where I was like, I don't know how to do anything. All of this stuff is just blank out of my head. And I'm like, okay, I need to calm down and figure this out. So then I followed his advice. I said, I'm stuck. I'm going to waste 20 minutes on this question. So, like, how am I going to do that? I'm going to sit here and just stare at this question for 20 minutes and barely get anywhere. So what do? I read all of the questions going through, and a couple of them I was like, I know how to do this, so I made notes immediately against his suggestion. But then I flipped through and eventually got to the end, went back to the beginning, and then started working on it, and I'm like, huh, okay. And in the same way that your brain, if you're working on a puzzle, you're working on a crossword puzzle, you see a clue that you're like, I know what the answer is, but it's blanking. Like, I just not coming to me. So you go through and you just start doing crosswords around it, and maybe it'll click. Maybe it won't. If it doesn't, you go off, you make yourself a sandwich, you go do something else for a while, you come back to it, and, a couple hours later, a couple of days later for that matter, you look at it and go, oh, well, the answer is, 53 or whatever. I don't know how I didn't know that, like, the first time I went through it. The point is that your brain is working on this stuff in the background while you don't know it. This is kind of where the joke about Lewis Black doing his if it weren't for my horse joke, like that's kind of the joke about this, is that stuff gets in your head and it starts working in your neurons, and then the correct neurons start firing if it's something that you know about. So if it's something that you are recalling, you could be like, oh, I remember that this is connected to that, is connected to that, is connected to that, and it starts firing off all the neurons and warming up those pathways. And eventually the correct chemicals get into the correct spot, and then it clicks, and you're just like, I know what that is. That's weird. Blank Gabor. Well, it's Jaja, clearly. Yeah, so the other problem with the time constraint, right, it ends up being that if you're in an ACT or SAT, that is another problem, is that you're only given access to a certain portion of the exam, so you can't go any further than that. So you can read through like the 20 questions or whatever that are on this section, but then you can't go back anywhere really. Hmm. Yeah, multiple passes on that. And again, you can get as far as you can within this like 5-page limit or whatever. But yeah, I really like the I liked the biology aspect of this because I was not a very great biology student in high school. There was too much memorization for me. It just didn't really mesh too well. But seeing biology in action like in this particular way. That was something that was really cool. The other thing that we did in neural networks was, let's see, we were, yeah, I haven't really used neural networks in the sense of like trying to figure out how to leverage. I mean, like I can try to leverage just general psychology, but I don't know that I'm like leveraging. I don't know that I'm leveraging neural networks toward learning something new for them, except that you need repetition and you need to see it from like different angles. One of the things that we did find out recently was like, oh, this is a Veritasium video. You are not a visual learner, I think was what it was called. Or at the very least, that was the sign that he was holding, was you are not a visual learner. And basically the idea was that there's no such thing as visual learners. There's no such thing as whatever. Yeah, yeah. And so for anybody who hasn't seen it, there is no such thing as a visual learner was kind of the point that he was trying to get across, which is a little inflammatory for people who are like, I'm a visual learner. But like so many people that he was talking to on the street said that they were visual learners. So what he did was he randomized them into a couple of groups and he had them do something that was, more visually oriented. And yeah, the biggest myth in education. And the other group he had done was like, I'll do some other method. So he did like a, auditory only. And then he did like, whatever else. And it turned out that the distribution almost ended up being the same across the board, where everybody did sort of okay at memorization of like a short list of objects. When they were looking at something, just reading it, and when they were seeing like the pictures, and when they were seeing or when they were hearing it, or whatever else they were doing. So the one method that they were learning was not great. It was okay, but there was some variation. Some of the people got all of them, but other people were like, oh, I missed one or two, or I missed like five. I only got half, something like that. So then he, after that, with every single person, after they did their one, learning style, he gave them all of the learning styles that he possibly could. So he like gave them pictures with the names underneath them. He gave them a list of just the names that he wanted in that particular order. It was like, flashcards and a list, and also had like somebody saying them out loud in that list order. And by the time that, at the end of the 1 minute or whatever they had, he gave them the test again, and every single person scored better. And it wasn't just that, oh, they knew the stuff because it was the same stuff. No, no, no. He like randomized the order of the things that were being asked, or had a separate list or something like that. But at any rate, the point was that every single person did better when they had a multimedia approach. So you need to focus in your classrooms, those of you who are teachers, in doing as many possible different methods as possible. So, get something to handle, get something to visualize, get something to see, talk about it, do all of the things. And when you do all of the things, everybody will learn better than any one person would do in any one learning style by themselves. So yeah, I absolutely love that video, and I will tout it to the end of the earth. I know several of my students have actually said, oh, I'm a visual learner in the past few days. And I was like, you need to watch this video. Okay, so anyway, now that we've gone on to like an hour-long tangent, See, this is why I can stream and not have to worry about anything. So we can just do this, and then yeah, whatever. We don't have any. We're not beholden to anybody. It's fine. All right. So where I had been going. Woo! Oh yeah, go for it. Ba-doop doop doo. Ah, there it is. Copy link. Post in chat. Ah, really? You jerks. It gave me the ridiculously long Google link instead of the actual YouTube video link. All right, here we go. There we go. As it auto plays in the background. Yep. Oh, did it eat yours? Because you're not like allowed or something? It's possible. I didn't even think of that. Sorry. Yep, no problem. It's I didn't even notice. How long is that? Anyway, not important. So, what I had been doing earlier was mentioning the fact that when I teach my students how to do um, uh, oh goodness. All right. When I was teaching my students how to do function transformations, there we go. Basically, this is any kind of function whatsoever which has a parent function that looks like this, whatever it might be. So it doesn't matter what it is. But then the linear transformations follow the exact same rule. So that is y equals a times f of b times x minus c plus d. So all of the linear transformations follow these rules. And then we discuss, like, what is it that all of these individual things do? So A is going to be its vertical stretch factor. So I will plug this into Desmos, like some random function, whatever it might be, whatever we're talking about that day. Plug this parent function in and say f of x equals this. Then on the next line, I will put this one right here. Y equals a times f of b times quantity x minus c plus d. When you do this, it takes the f that you assigned up above, which in this case, right, it does use it as an assignation. That that f of x is assigned as 3 to the x. Hey, I feel like YouTube would be a safe thing, though. I don't know. Considering it's stripping away everything, like I don't think you can put HTML in chat, right? Like, I mean, don't try, but it was coming from the streamer, so. All right, so A is a vertical stretch factor. So whatever and so this is the thing, the distances, I always stress this. This is the, could be a stupid video, right? Like, not even naughty. It could be a stupid video, like, one of those, uh, kid crack, the kid crack videos, the finger family or whatever. God, I hate those videos. We had to strip. I mean, we didn't know any better, so we gave our daughter like access to YouTube, and she was like just clicking through at some point. Oh my God, it was so awful. She was just following one to the next, and it was just follow on stuff, and it always inevitably spiraled into one of these one of these videos because it was just something she was interested in. We're like, no, absolutely not. Here's what you can actually watch. I mean, it was family friendly. Don't get me wrong, right? The ones that she was watching were family friendly. They were just stupid, mindless nonsense that did absolutely nothing to teach her anything. No, she didn't have autoplay. We disabled that. But she would just do follow-on stuff that eventually spiraled into some sort of, some sort of clickbait, money-making nonsense that just wasn't educational, but it bills itself as educational. I'm just like, all right. Anyway, so then D, I don't want that one. D ends up being a vertical shift because here you're taking your function, and whatever's coming out as output ends up getting some number added to it, but it's uniformly added. So it doesn't matter what the size of any of these other values is. It's just going to take this whole function as it is and shift everything up by D. Which also means, if it's negative, then it's going to shift it down. So A is a vertical stretch factor because this does depend on how far away it is, right? So vertically speaking, we're measuring the distance, and I keep stressing that this is all about distance. We're measuring the distance from the function down to the x-axis, where the origin point is. So don't think of it necessarily as the x-axis, but rather as y equals 0, which is where the origin point is. Once you shift your origin point, in this case down 4, then the distances that we measure are going to be from that new origin point. All right, so C then is going to be a horizontal, first of all. And it is a shift, but it's in the opposite direction that it shows up as. Why is that? Well, if you have in here x minus 1, what are you doing? You're taking an x value that you pick, so this x value, and I'm going to go minus 1, so 1 back from that. That value gets plugged into the function. We get a y value. That y value then gets pulled to where my x value actually is that I'm asking for. So it just shifted to the right 1 space. So that's why x minus 1 on the inside of a function shifts right 1 instead of shifts left 1. You're treating your x values as if they were 1 smaller, and those y values get shifted up. And then the b value is always tremendous amount of fun. So first of all, again, horizontal. But here, when you're raising the b value, you're making it larger, you are treating your x values as if they are larger than they actually are, which means that, again, and you're multiplying your x values. So all of them that are away from the away from the y-axis get bigger by that factor. So they will double, they will triple, they will get cut in half equally, but the distances that produces are all going to be different numbers going across. So here if you say, 2x, right? 2x on the inside of the function, that means I'm going to double both of my x values, and these y values get plugged in the function, and they get returned to the x values that were here. So now all of the stuff has been crushed inward. So we have a horizontal compression factor. So I leverage English in order to show the students what it is that this is doing. So vertical stretch factor is saying, like, as we get 2, 3, 4, 5, this is going to take those distances and stretch them upward. As we take a horizontal compression factor and we make that 2, 3, 4, 5 on the inside of the function, this is going to crush inward further and further and further. So again, stretch for A, compression for B. So we're leveraging language. So in this particular case, the distances that we're used to for y equals 3 to the x are these things here. We are going to increment our x values by 1 and multiply our y values by 3 for that increment of 1 on x. So then over here, it changes. We're going to look at this and say, okay, first of all, where does it get shifted to? So our shifts are the -3 on the inside of the parentheses and the -4 on the outside, or rather -3 on the inside and a -4, -4 on the outside. So this is going to shift our function 3 to the right and 4 down. And this is still going to be going up as an exponential function. Let's go with here. No idea if this is going to work for us, but sure, why not? All right. In addition, this is going to have a horizontal compression factor of 1/4, which means that everything is going to be relaxed by a factor of 4 for the distance. The other way to think about it is that in the exponent, in order to increase the exponent by 1, you need to increase x by 4, due to the fact that we have this 1/4 multiplied here. Another way to think about it is that this is y equals, if we go back with the parent function, this is 3 to the x over delta x. Oftentimes is how we write this. So we divide by delta x. Delta x is going to be 4. So that means that our change in x as we go across is going to be 4. So now, let's see. Yeah, that'll be fine. So we'll go like this, and we'll say that, yeah, this will be 4. That's fine. 8, 12, and 16. It's going to go off the map too early, but whatever. It's good. Which means that at all of these half marks, these are going to be divisible by 2, but not 4. And at each of these are kind of about 1s. All right, and then up and down, we want, again, like 27. So what did I do? I did 8s before. This is multiplying by 2. Yeah, 8s could work. 16s could also work, although that's going to be a pain. Let's... Yeah, I moved this so far that it's just going to be a lot of blank space. All right, let's just do 4s. It's going to be ridiculous. It's fine. Those are totally negative. I don't know what you're talking about. All right, so then when we go through this, we moved our origin point to, again, 3, -4. So at 3, -4, this is where our origin point is. For the parent function, that's over that away. Right, we have our origin point at 0, 0. This is where the asymptote is. So our asymptote here is going to go through y equals -4. Or it is y equals -4. So there's nothing technically there, but we'll just use that. Okay. Then our initial point is, or has, a distance of 1 from the origin point in the parent function. In the transformed function, it has an initial value of 2. The distance is going to be doubled in the vertical direction. So here, This is going to be a distance of 2 away. It's going to be right there. So this is at 3 comma negative 2. All right, so 3 comma negative 2 is our initial point. Then we want to get the rest of the functions. Now here's the thing. You don't have to use a calculator and plug all this stuff in. You already have all the information you need just by placing the origin point, the initial point, and knowing what the pattern is for the parent function. Because with exponential functions, every time we iterate or increment, every time we increment our x values, our y values are going to multiply by some value. And let me restate that. The y distance is going to multiply by some value. So here we have a distance of 2 to start with, and then as we increment x by 4, y is going to triple. The distance is going to triple. So here we have a distance of 2. So if we go 1, 2, 3, 4 over, this is going to triple this distance from 2 to 4 to 6. Then, if we go the other way, we iterate, we increment, we increment by 1, 2, 3, 4 in the x direction, and now our distance gets cut in thirds. So instead of here, a third is right about there. If you want to measure the exact value and actually put in an exact point, you can do that. In fact, when I'm writing all this stuff, I don't label it, because I know exactly where these points are. The distance here is going to be 6. Okay, what's the distance then? This is going to be from negative 4 up 6 is positive 2. And then we're at an x value. We incremented once from 3, makes this 3 plus 4 is 7. So yeah, 7 comma 2. I'm only going to actually state the actual point if I need it. And honestly, I don't most of the time. All right, and then again here we go 1, 2, 3, 4, and then cut this by a third as well, and that goes in there. And then we just keep doing the same thing. So this is going to get cut in a third down here. It's going to get cut in a third down here. So our distance keeps getting cut in thirds, and it keeps getting smaller and smaller. And then after this, our distance here is going to get tripled from 6 to 18. So the 18 is a little bit big, but we can make it work. This is going to be incremented by 4, so we're up at 11 now. And then we're at a distance of 18. So this is 6. That's going to be 10, 14, 18. So we're here. Not that I recommend necessarily graphing all the way out there, but at least know where it is. All right, so that goes up that way. That goes out that way. Again, we've got nice dotted asymptote leading off that way. This is now the transform function. Y equals 2 times 3 raised to the 1/4 parentheses x minus 3, all minus 4. And then you can, of course, go into Desmos, your calculator, whatever, and check to make sure that that's correct, because, you know, I've been known to screw up. Famously been known to screw up. Yep. And like so I actually did one with my students last semester, and they flipped out when they saw it, because it was like y equals 1/3 natural log of, oh, you know what? It was absolute value, 4x minus 3 plus 7 or something like that. And they're like, what the hell? What are you doing? Like, why would you do this to us? And I'm like, okay, seriously, go back, figure out what all of the stuff is, figure out the parent functions. You already know how to do transformations. Yeah, there's some fractions in there, but guess what? Life isn't always going to work out with nice integers. So they worked it out, and like 10 minutes later, they're all like, oh, huh, this was actually kind of easy. I'm like, there you go. But like, yeah, there's no difference between the difficulty of this and the difficulty of this. Like, not really. It's pretty much the same. You got to figure out where the origin point is. You got to figure out where the initial point is. You then got to figure out like what the pattern is to go from one point to the next, and that's it. So natural log is a little bit harder to figure out what the pattern is. You're just multiplying by, 2.7, 1828, 1828, etc. So, figure it's about 2.8, figure out what that is in your calculator, or literally just plug it into a table. Like this is not difficult. All right, anyway. Oh, the other thing that oh my god. I was so upset by this. I went and I was like, okay, last semester we were teaching so last semester we were teaching the quadratic equations, right? Just how to solve them, what the properties are, all that stuff. And I went through the stuff we did over there, where you say, okay, this is y equals a times parentheses x minus c squared plus d. And we had worked out that actually b doesn't matter, right? Because if you did this stuff, b times x minus c squared plus d, then you can bring in the square and make this a times b squared times parentheses x minus c squared plus d. These two combine to an arbitrary constant a. X minus c squared, oops, x minus c squared plus d. So my thing was, if you've got some convenient way to split up these numbers, like your a value, into a perfect square and a not perfect square, I'd suggest doing this and then deal with b as a horizontal compression factor. I like it. I don't know. Rather than like... So this is the other thing, is that rather than multiplying your a value of like 2/3, I mean, 2/3 I'd have to deal with it as 2/3. That's okay, I guess. But if it were 2/9, right? I wouldn't put up with that. I'd be like, okay, 2/9 is awful. I'm going to make this 2 times 1/3 squared. And then say that this is going to be 2 times parentheses 1/3 times the quantity x minus c all squared. If you take in that 1/3, now it's a horizontal compression factor of 1/3, or you're multiplying all of your x distances by 3. You're tripling all of your x distances. Makes it much easier. All right, so I was saying, okay, let's find the intercepts of this thing. And again, for the y-intercept, this is nice and easy. You plug in 0, you end up with a c squared. And again, this is the other thing, was that the other form of the equation, the expanded form, is y equals ax squared plus bx plus c, because some genius decided to reuse these for these things. So this comes from expanding out all this stuff, and the constant function y equals a, and the linear function y equals ax plus b, and then the quadratic function is y equals ax squared plus bx plus c. So naturally, this just kind of follows the same progression. You're just going to keep increasing the number of letters that are here, and you're just using a, b, c, etc. Well, using a, b, c, etc. is not great if you're going to do this the exact same thing, and c and d in this context have no relationship with the c here and a d if it were a cubic, right? They are not the same thing. I mean, they're slightly related, but not like that. So what they did was they said, okay, your vertex is going to be at h comma k. So instead of c and d, they erase this, and they put x minus h and plus k on the outside. Then they say, okay, intercepts are going to be, if you plug in 0 for x, you get negative h squared, which is just going to be h squared, times a, so a h squared plus k. Yep. Whereas in this form, it becomes much nicer because your intercept is just going to be 0 comma c. Woo. So, I mean, both of them technically are a translation. But yeah, I get what you mean. Like horizontal, that's probably why it's h, huh? Huh. Horizontal, and I have no idea why k is in there. Superbrain, how about how about German? I know constant is usually a good one to use for k. Would any... I can't think of any like words that would start with K that would have to do with moving it up and down or finding the vertex of a parabola. Yeah, I can't think of anything. Anyway, I was doing the intercepts like this and finding, again, y-intercept. And then we get to x-intercept, and I'm like, okay, you all know how to do this because you've just memorized the quadratic formula, but let's just stop, right? Let's just stop this x-intercept thing. Let's not memorize it, because, again, memorization is stupid. Let's not do it. And up here, we say, okay, how do you find the x-intercepts for this? Okay, you plug in 0 for y. What does that leave us? Well, that's 0 equals a times x minus h parentheses squared plus k. How do you solve this? Well, subtract k. Then when you subtract k, you've got a times this stuff, so we can also divide by a, leaving us with parentheses x minus h squared. Okay, take the square root of both sides. Here we have the absolute value of x minus h is equal to the square root of negative k over a. Thought somebody woke up. Okay, then from here, this is going to say, well, if we have absolute value of x minus h, we can rewrite this. Typically, I force my students to rewrite this as the piecewise function. So x minus h if x is greater than or equal to h, or h minus x if x is less than h. And then it breaks down into two possibilities. For this particular case, I usually say, okay, well, the absolute value of x minus h is going to tell us that this stuff over here could either be positive or negative. We don't know which. Or rather, no, sorry. The stuff on the inside, x plus h, could either be positive or negative. We don't know which. So that means that x minus h will have a value either of a positive or a negative. square root of negative k over a. Then when we do that, we're going to add h to both sides. And we get x equals h plus or minus square root of negative k over a, where h and k are going to be the, again, x and y values of the vertex, and a is going to be the constant multiplier out front. And I looked at this and I said, why don't we teach this? Why isn't this the exact thing that we teach all students all the time? Because you can find the vertex pretty easily, right? We've gone through all of this stuff. So this also means that we know how to find the vertex. The vertex is h comma k. And if we multiply this thing out, we get y equals a times the quantity, x squared minus 2hx plus h squared plus k. This is equal to ax squared minus 2ahx plus ah squared plus k. Well, here's your a. It's a. Here's your b. And here's your c in the expanded form. So ah squared plus k, we already did that for the intercept. We know that that's equal to c. And then how do we find the vertex? Well, the vertex is at h comma k. How do you get h and k? Find out what they are in these equations. Right here, you've got negative 2ah is equal to b from the expanded version. So then here, if we're trying to solve for h, this is going to be divided by negative 2a. H equals negative b over 2a. Anybody who's ever studied the expanded form knows that that's what that is. Okay, that's h. Cool. What's k? K is equal to, well, okay, let's back that up. C is equal to ah squared plus k. So k is equal to c minus ah squared. And h is equal to negative b over 2a, parentheses squared. When you get this squared, it is going to be c minus a times b squared over 4a squared. One of these a's divides out. So k is equal to c minus b over 4a. Yep. Right? This is so much easier to be able to figure all this stuff out. If you end up with... Now, I don't recommend, like, memorizing this. The h equals negative b over 2a, that's something that people just memorize anyway most of the time. But the other thing is that if you wanted to, like, find the x-intercepts in this expanded form, right, you already know how to do it. You already know what the result's going to be. It's going to be x equals, h is negative b over 2a, plus or minus the square root of negative k is, parentheses, c minus b over 4a, all over a, which is negative b plus or minus this square root over here. You know what? I'm not doing that yet. Negative b over 2a plus or minus the square root of this part is going to be reversed from the negative, so a negative c and a positive b over 4a all over a. Multiply both top and bottom by 4a to get rid of this stuff. Get rid of the compound fraction. This is negative b over 2a plus or minus square root of b minus 4ac, oh look at that, all over 4a squared, which can be taken, we can take the square root of that to be just 2a. So negative b over 2a plus or minus square root of, uh-oh, I missed something. Oh, that's b squared, right? B squared. I knew something was wrong. All right, b squared minus 4ac, which we know is the discriminant, all divided by the square root of 4a squared is 2a, and then you can combine. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? Right? Like, I saw this. I saw how to find this stuff to get H and K, and I was like, this is so intuitive. Where's this been all my life? Like, in high school, when I was in Algebra 2, I think what we did was we started with the expanded form. So we started with this expanded form. We found out all the properties for it. We found out that if we decided to use completing the square, if we did completing the square, we could work our way backwards to this thing, to the vertex form. But like, yeah, you're completing the square, but like, so what? No, I'm not saying like memorize the formulas, right? I never say that. I'm saying if you already know what the vertex form is because you have spent the entire semester talking with some crazy guy about how to do function transformations, and then we want to find the x-intercepts of this particular equation, right? This thing just drops out instantaneously. That's the quadratic formula. But all you need to know is where's the vertex and what's the a value. That's it. Nothing else. So if you have this thing here, your expanded form, yes, you have to do a little tiny bit of work for it, but you don't need the formula to do it if you remember how to do it, right? So h, the x value for the vertex, is going to be negative b over 2a. Maybe you need to remember that one, or maybe it's already given. Is that Machane? Thank you for the follow. I am looking to get the actual audio from Square One TV to play over that instead of just a blunk. I'm looking forward to trying to fix that. Unfortunately, this morning when I tried to do it, my I have Audacity, and it has the audacity to not accept internal inputs immediately, and like, it's such a nightmare. I can't remember. Every time that I open Audacity, I have to switch this, and I don't remember how to do it every single time. And like, it's on. It says it's monitoring it, and it also is like on the correct thing. But I need to add like one of the audio settings somewhere deep inside the... I don't even remember. It's just insane. It never works the way I want it to. Let's put it that way. Okay, anyway. Give me 1 second. Let me see if I can... We'll see if that does it next time. So I muted it from a different scene. So in theory, that scene is not supposed to be in use, but at the same time, I think it is in use and it's still accepting inputs. So that might be why we're getting two little blink sounds. Either that or stream elements is messed up, and that's fine too. You know, I'll figure it out someday. Okay. Yeah. So anyway, finding all this stuff, I was just I did that. I did that today for my classes, and I'm just like, oh yeah, that's probably it. Yeah, it's probably browser audio, and then it. I don't know, because if it did that, I definitely have desktop audio on. It might. I'm not sure. I'm just thinking, like, if it did actually do that, wouldn't it do it an infinite number of times, or um, exponentially decrease? I don't know. Instead of just exactly twice. I don't know. Seems like it wouldn't. Doesn't particularly matter. Anyway. So yeah, I was telling my students today in my pre-calc class that, like, this is kind of the way that I want you to think of this more. You all pretty much know this quadratic formula at the moment, but, like, it doesn't really help to just have it if you don't understand why it works. And trying to start from here and then do completing the square to get to here was a little counterintuitive, considering we've done stuff here all the time. Like, the entire rest of the semester, our quadratics are always somewhere in there. Uh-huh. Okay. No, that's fair. Properties. Ah. Let's see if... Don't know if that's going to do it. Alright, I am muting stream elements audio inside of OBS. Don't know if that's how that works, but sure, why not? Let's try it. Anyway, yeah. So we were doing properties of quadratics today with the pre-calc class, and this came up because I was just like, all right, let's seriously look at this and do this. Let's not worry about the expanded quadratic form as much, and we'll see more examples of this stuff when we get further on. But at the same time, anytime that you want to go back to this one, it's actually fairly simple to work it out. And again, you don't need to do all of this stuff. The k equals c minus b squared over 4a, what's that? Well, that's just plugging it back into the equation in the first place. So, yeah, just doing f of h, f of negative b over 2a. All right. Anybody got any questions? I mean, y'all have had a lot of questions, so it's pretty awesome. Yeah, thank you everybody for coming. Um, we've had a lot more people in today than ever previously before, so thank you. It's like doubled our usual and like tripled the average. So that's been great. I think we are probably winding down here, and I'm gonna hop into somebody else's. Let's see who's actually on tonight. Let's see who's still on tonight, I should say. We have Jason Charles Miller doing whatever you want Wednesdays. He is a rocker and a person that I have admired from his days at Geek and Sundry. He has been working a lot with the Q Times people now, doing tabletop RPGs and music for tabletop RPGs on Q Times. So I think that is where we're gonna go tonight. Just because, again, Jason's kind of a person that we usually head on over to. He's a great guy. And if you enjoy music of all varieties, he's definitely a guy to check out. So, thank you very much for coming, everybody. And we'll see you next time. This is Obi-Wan Pez for N Simplex Pachinko. We'll start this off. Got just a few more seconds here. No problem. And Machine, if you have any questions, let me know. I can also be reached at channel name and Simplex Pachinko at gmail.com if you have anything that you want me to look up over the week, or otherwise you can come back and see me here probably next Wednesday, barring anything weird happening. I am also here on Fridays for gaming, so we are doing let's see. I'm going to be doing a special stream next week on Tuesday because the DLC for the DLC for Outer Wilds is coming out, and I am like seriously hyped about it. So we're going to be doing a special stream on Tuesday. That's just that game. I have no idea how far I'm going to get through it, but we'll see. And Friday we're going to be doing probably more Astroneer for the event that's going on right now. So anyway, thank you very much, and see you later.